Okay, let's try again. Marija, do you hear me? Oh.
I can hear you. Yeah, now I can hear you. And I guess you can see me now.
I can see you. It's Martin here. Nice to see you.
I recognize the voice, don't worry. Do you see the slides?
Oh, yeah, we see the slides. Everything is fine. So,
okay.
Now we're ready for your talk. So, please welcome Marija Dimitrijevic Ciric. And the title is Infinity Algebras and Braided Field Theory.
Okay.
So, 25 minutes plus questions.
You will let me know when there is like 10 minutes or 5 minutes till the end?
I can do that.
Okay, that will be perfect.
Sure. Okay, then let's go.
Okay, thanks a lot. So as usual, let me thank the organizers for the invitation and the possibility to present our work in this workshop. And I guess from the title, it might not be obvious what the talk is about, apart from the L-infinity part there. So I will speak about yet another way to introduce a non-commutative gauge theory and how this is related with the concept of L-infinity algebras. And I guess this is the only talk about non-commutative field theory in this workshop. But okay, it will fit somehow. The work I'm going to talk about has been done in collaboration with Richard Szabo and his PhD student Grigorios Yotopoulos from Edinburgh, and with my colleague Voja Radovanovic from the University of Belgrade. And quite recently, we have two junior researchers from University of Belgrade that joined the collaboration, Nikola Konjik and Misha Toman. So let me tell you how the talk will look like, more or less. So I start with the motivation, which I somehow divided in two parts. General motivation, the usual one, and one motivating example of how we are going to define, let's say, this new non-commutative gauge theories. Then after this motivation, I will speak about L-infinity algebra. I will not go into too many details concerning classical L-infinity algebras because we had a very nice review talk this morning by Olaf Holm, and he explained everything. So I'll be very briefly about this classical part, but then I will explain, or at least try to explain, how we deform this concept and adjust it somehow to the non-commutative field theories, and that will be something that we call braided L-infinity algebras. And then finally, I will give an example of braided electrodynamics as a non-commutative braided field theory that is related with this concept. So, general motivation, we start as usual. So we know that we should look for something that is quantum gravity at small scales and high energies, and we somehow believe that there is a notion of quantum space-time at this very small scales, high energies, and one of the possibilities could be that this quantum space-time is a non-commutative and or whatever you prefer, non-associative space-time. And there are all sorts of different ways how one discuss field theories on these non-commutative spaces. And there is a work of, like, for example, Alan Kohn on spectral geometry, non-commutative spectral geometry. Then there is the operators and representation theory work done by John Mador, Sean Majid, and the others. And next week, there will be a workshop, non-commutative, let's say, workshop, which is dedicated to John Mador. And then there is the deformation quantization, which different people worked on that. We all know about Koncievich, formality map, and so on. Whatever you do, when we go to non-commutative spaces, there is the concept of space-time symmetry that is relatively difficult to generalize. And we somehow stumble on this concept. We either ignore it or we try to say something about this. And luckily for us, there is this Drinfeld field twist formalism, which is a well-defined way to deform a symmetry Hopf algebra to a twisted symmetry Hopf algebra. And we use it like in the last 10 to 15 years, I think we have been using this Drinfeld twist formalism to consistently define symmetry algebras like space-time symmetry, for example, the diffeomorphism symmetry of general relativity, and then consistently using, again, this Drinfeld twist to deform the differential geometry, if you want, or module algebras on which this symmetry acts, like differential forms, tensors, and so on. And we somehow define this notion of non-commutative differential geometry. So this dreamfield twist formalism I will use in this talk, and I will just briefly sketch it, I think, on the next slide, just to introduce the notation. I will not bother you with that too much. The other concept that we are going to use is the concept of L-infinity algebra. And we saw this morning in this review talk by Olaf that any classical field theory can be fully described by its corresponding L-infinity algebra, and all the data like equations of motion, second and third identities, symmetries are encoded in this L-infinity algebra. And then one might wonder what happens with the non-commutative field theories, how they fit in this concept of L-infinity algebra. Should we somehow deform the concept, or we work with a classical L-infinity like Olaf was describing? And if this is doable, do we learn something new? Are there any new insights that we learn from trying to fit a non-commutative field theory in the L-infinity algebra picture? So, sorry, this was not good. I can do it like this. The twist deformation, like I said, I will try to be very briefly about this. So this is the approach, if you want, defined by Dreamfield, I think in the 80s. And it's a consistent way to deform Hopf algebra of your symmetry algebra. So you have a symmetry algebra G, then you define its universal enveloping algebra, and then this universal covering algebra UG has a Hopf algebra structure. And then one defines this twist operator, which lives in the two copies of the universal covering algebra and has to fulfill certain requirements like the co-cycle condition, and it has to be invertible. And additionally, we always require that this twist starts with a unity and then has high order terms in the deformation parameter. In this way, we ensure the commutative limit. So when we put this deformation parameter of non-commutativity to 0, we always recover the classical, if you want, the classical symmetry, because at the moment we are speaking about symmetry, which somehow we like. Then this twist defines the R matrix, and we will always work with twists that define triangular R matrices, meaning fulfilling this. And just for the notation, the inverse of the R matrix we label like this. It also lives in the double copy of the universal covering algebra. And the R matrix itself is something like this. So the principle goes like this. We have a symmetry Hopf algebra, or universal cover of it. We twist it to the twisted symmetry Hopf algebra. Then the algebra in principle does not change. The coproduct changes, leading to the changes in the Leibniz rule of your symmetry transformations and so on. The antipode might change, might not, depends on the particular choice of the twist. The module algebras that your symmetry algebra acts on, like functions, differential forms, whatever, fields, they get deformed to star module algebras consistently, in such a way that whenever we have objects that live in A, which is a module algebra, there is the usual product in this module algebra. We apply the twist and we define the star product of these two elements. And the star product is defined by precomposing the usual product with the inverse of the twist. And then this star product is not commutative. The non-commutativity is encoded by this the inverse essentially of the R matrix. So A star B is no longer B star A, but there is an R matrix appearing here. So I guess here it's enough that you remember that whenever we have a star product, we know that it is non-commutative. We will work with associative star products. One can also work with non-associative, but for the moment at least in this talk, in this work, we concentrate on associative star products, or the twists that fulfill this two co-cycle condition. So whenever there is a star product, it's non-commutative, and if you want to change the order of the elements, there is an R matrix, the inverse of the R matrix appearing here. So this is something that you might try to remember. For example, the well-known example of a twist, and a very simple example, is the Moyal-Weyl twist that gives rise to the Moyal-Weyl star product. So you could say that your symmetry algebra, for example, is either diffeomorphism, so you have the full algebra of vector fields, or for example, a translational symmetry in the Minkowski spacetime. Then you have this derivatives. This is actually, they generate translations. And then the twist is, so it lives in the two copies of the universal covering algebra of your translations. And then this is the corresponding star product defined with the inverse of the twist. It's not commutative, there is an R matrix, and that's it more or less concerning the notation. Now concerning this motivating example of two commutators, as I called it. Once we have the star product, or we know how to deform module algebras, we introduce the full concept of differential geometry and so on. One might wonder, how do we deform gauge theory? So we start with a non-abelian classical gauge theory. This is the gauge field, the transformation law of the gauge field. The rho is the gauge parameter, and it's some arbitrary non-abelian gauge symmetry. How do we transform this to this star product approach? And essentially, we learned now that there are two ways. One way is to do what we call now star gauge theory, and that is the usual way. So the idea is to promote these gauge transformations into star gauge transformations, putting star in this commutator, saying that instead of the usual commutator, now we write rho star A minus A star rho. And these gauge transformations, they have the usual Leibniz rule. We worked with them quite a lot. The problem with them is that this star commutator defined in this way does not close in the Lie algebra. For almost all examples that you need in physics, it closes if you work with the UN transformations in the definition, in the fundamental, let's say, representation, but it does not close for SUN groups, and you need SUN groups for particle physics, for example. So the way to close it is to go to the universal enveloping algebra, which is infinitely dimensional, and then the star commutator, of course, closes there. But then you have a problem of infinitely many degrees of freedom, new degrees of freedom, which essentially we don't see phenomenologically. We don't see them in the experiment. And then there is the whole story of Seiberg-Witten map, which enables us to get rid of this new degrees of freedom. We just express them in terms of the usual commutative degrees of freedom. And that works, where one can do a lot of things with that. The problem is that this way of deforming non-commutative gauge theory, defining the star commutator in this way, is not really compatible with the twisted space-time symmetries. So if we use the twist formalism to twist, for example, either Poincare symmetry of Minkowski space-time or the diffeomorphism symmetry of general relativity, then the twisted space-time symmetries look a bit different compared to the star gauge symmetries, and there is a clash between these two things. And that we learned when we tried to work consistently the gravity in the first order formalism, because there you have a diffeomorphism symmetry and you have the local Lorentz symmetry, which is a gauge symmetry. And if you treat local Lorentz in this way, then there is somehow a clash. And in particular, L-infinity structure is a bit difficult to define. Nevertheless, the L-infinity structure of this kind of non-commutative gauge theories was discussed in papers by the Munich group in 2018. And they managed to construct order by order infinite dimensional L-infinity algebra with infinitely many brackets. The problem is that this construction is really order by order, and the higher orders you want to construct, the more complicated it gets. But in principle, it's doable. And the other nice feature about the symmetries is they really naturally appear as a low energy limits of string theory. So maybe that is one of the reasons why we like them, let's say. So the other possibility, if we are not quite happy with this clash of space-time symmetries and the star gauge symmetry, is to introduce something that we now call braided gauge theory. And that means especially that this commutator is now defined in a different way. The star commutator, first of all, the star is no longer in the middle, it's now in the right lower corner. And what we mean by this is that we multiply rho and A, but then when we exchange the order of A and rho, we just add one R matrix. And this R matrix is crucial because it enables this braided, now we call this commutator braided commutator. This braided commutator really closes in the Lie algebra. It's somehow funny, but it does really. One can check, one can really write explicitly the gauge parameter and the gauge field in the Lie algebra, calculate what it is, the star product and the R matrix, and it comes out that this reduces to this. So it's just the star product of this X-dependent part and the Lie algebra part of your gauge group. So that's nice. We don't have infinitely many degrees of freedom. We don't have to go to the universal covering algebra and so on. We stay just in the Lie algebra. The thing that is not maybe so appealing is that these symmetries, they have Leibniz rule, which is not the usual one, but it's braided, deformed, non-commutative, however you want to call it. So when this transformation acts on the star product of two fields, it acts on the first, but when it's supposed to act on the second, then it somehow has to commute through the first field, and then you get an R matrix acting on the first field and on the gauge parameter. So this Leibniz rule is, it's not a new completely Leibniz rule, because it appeared early in the work of Voronovich and Marija also on quantum Lie algebras, for example. But I think for the gauge field theory, it's something that we haven't used so far. So this might not be very nice, but nevertheless, it closes in the Lie algebra, and that is why we like it. And now, and of course, the other thing that we like very much is that this way of defining non-commutative gauge theories is compatible with the twisted space-time symmetries, because, for example, twisted diffeomorphisms, they also have this kind of Leibniz rule. There is a bigger chance that we might construct something more consistent in this way. And we, of course, wonder what is the L-infinity algebra structure of this, because this hasn't been analyzed so far. So in the rest of the talk, I will concentrate on this braided gauge theory. And I will try to introduce it using the concept of the L-infinity algebra. So I go to the L-infinity algebra. I don't want to go into too many details. We saw, like I said, the talk of Olaf this morning. L-infinity algebras, also known as strong homotopy algebras, they appeared in mathematics and in physics. And we saw that all classical field theories, they can be described in terms of L-infinity algebra. I mentioned that non-commutative gauge field theories can be described in terms of L-infinity algebra, discussed by the Munich group and Vlad Kupriyanov. But then, okay, with some problems that I have already said. And what we did with Richard and with Gregorius and Voya is that we constructed the L-infinity algebra of the Einstein-Cartan gravity, so the first order gravity. This is the classical L-infinity algebra. Olaf was showing this morning the L-infinity algebra of the general relativity, so he had to do it perturbatively. He expanded around the fixed background and then constructed L brackets order by order. But if you do it in the first order formalism, so you have the spin connection and the Vierbein, then one can construct really nicely the L-infinity algebra picture, which is fine. In 4 dimensions, you only have up to L3 brackets, for example. Then what we also did, we also constructed the L-infinity algebra for the non-commutative gravity theory, and there the concept of the braided L-infinity algebra appeared, and that is what I will try to introduce. Just to remind you, the classical L-infinity algebra, we have a Z-graded vector space, we have Ln brackets that map n copies of the vector space to the vector space. They are graded antisymmetric, meaning that when we exchange the order of 2 elements in the bracket, we get a minus sign depending on the grading of these 2 elements. And these brackets, they are not arbitrary. They have to fulfill infinitely many in principle homotopy relations, which can be seen as a generalization of the Jacobi identity for the ordinary Lie algebra, because it's essentially L-infinity algebra is a generalization of the concept of the Lie algebra. And additionally, we need a cyclic pairing because we want to construct an action. So we need a pairing that will give us a number, basically. And this pairing has to be cyclic because we want to use the variational principle to be able to extract equations of motion from the defined action. How does it work in the gauge theory? So we say we have gauge parameters that live, for example, in V0, gauge fields in V1, equations of motion that take values in V2, and the second Noether identities or Bianchi identities, which are the differential identities that connect the equations of motion in V3, and then the gauge transformations, they can be written as infinite sum over L brackets, starting with L1 and then so on. Equations of motion in the same way. Action can be written in terms of this cyclic pairing, also infinite sum of the brackets, and then the Noether identities also, they start with with L1 of the equations of motion and so on, so on. The variational principle, so these equations of motion, they really follow from the variational principle if you use the cyclicity of this pairing. So you start with this action, you vary the field A, and you really end up with the field equations like this. And now the question is, we know how to use the Drillfield twist formalism to deform symmetries to deform module algebras. Can we use the Drinfeld twist formalism to deform also the L-infinity algebra? And the answer is yes, we can. The question is, do you really want to do it? But let's say we do want to do it because we need it for our work. And essentially, what would be a braided L-infinity algebra? It would be a generalization of a quantum Lie algebra, which was defined by Voronovits and then later on by Majid. Like the classical L-infinity algebra is a generalization of the classical L-infinity algebra is a generalization of the ordinary Lie algebra. Then this braided L-infinity algebra should be a generalization of a quantum Lie algebra. Rigorously, the braided L-infinity algebra can be defined in terms of this monoidal category and so on. But this, I don't want to go into details concerning this. I just want to explain how in practice this works. So we start with the same Z-graded vector space. If you remember from the previous slides, like gauge parameters, gauge fields, equations of motion, and so on. And then we have brackets.
Slightly less than 10 minutes.
Slightly less or more. Okay.
Around 10 minutes.
Around, okay. So these brackets, now we deform into star brackets, saying that we precompose it with like in the usual way, like we introduce the star product, we introduce this inverse of the twist. And then the brackets are now graded antisymmetric, but they're also braided, meaning that when we commute two elements, there is also an R matrix appearing there. And the simplest example, for example, in this non-abelian gauge theory, for example, Chern-Simons, there is an L2 bracket, which is just the commutator. And if we use this rule to deform this L2 bracket, then it will really be a braided commutator, the one that I had in my example, like the second example. Homotopy relations, they also change. The changes you don't see in the first two homotopy relations. In the third homotopy relation, there are some R matrices appearing there depending on the order of the fields. Like when you commute 3 and 2, there is an R matrix and so on. And the cyclic pairing also has to be defined consistently. So normally when we define it in such a way that we precompose it with a twist. And then it's naturally this, if we have a pairing between V2 and V1, then it's naturally braided symmetric or braided cyclic because of this R matrix, but we need a more strong requirement because of the variational principle and the equations of motion. And then we demand something that we call strict cyclicity. We demand that this R matrix disappear from there. And then the twists that fulfill this kind of condition we call compatible Drinfeld twists. And it's not so difficult. Moyal-Weil twist is, for example, compatible. It sort of reduces to the cyclicity of the star product under the integral. Who knows something about that? It's similar to this. The braided gauge theory is now defined in the same way as the usual field theory. We just put star brackets. So we have braided gauge transformations, braided equations of motion, braided nether identities. They're a bit different, because now they don't follow from the symmetry of the action, from the variation of the action, but they're essentially a combination of homotopy relations, a non-trivial combination of homotopy relations. And what is new there is that, for example, for the Chern-Simons, braided Chern-Simons, if you want, these three terms, they really depend on the equations of motion, and they're homogeneous in the equation of motion. And if you take the classical, the commutative limit, they reduce to the classical Bianchi identity, but there is a fourth term which is inhomogeneous in the equations of motion. It depends only on fields, and that is something new. So we have already something new on the level of braided nether identities. One can define the braided action, show that it is braided gauge invariant. Here I wrote the example of the three-dimensional Chern-Simons, and what I wrote here more or less that this. For Chern-Simons, for example, we get what we would naively expect as a deformation. We have stars everywhere. The only difference is that this star commutator is now the braided star commutator. I think I will skip this for the moment, and I can later go back to this. So three-dimensional Chern-Simons is relatively simple because it has L1 and L2 brackets. In the four-dimensional non-commutative braided Einstein-Cartan gravity, we also have L3 bracket, and there, because of the L-infinity structure, so we define an action in terms of L-infinity bracket, we also have some terms that you would not naively expect from your deformation. For example, these two terms are something that you would expect. You just put stars in your commutative Einstein-Hilbert action. This is the cosmological constant term. However, there is the whole line of new terms, which you would not write by somehow. They are unexpected somehow, but they follow from the L-infinity structure. And that is something that L-infinity algebra really gives us new. So the deformation of the action is something that you would not expect. It does not reduce it to just put stars everywhere and work with this. There are new terms. Finally, the electrodynamics, which is a much simpler example than this four-dimensional Einstein-Cartan gravity. It's just the usual electrodynamics. It's a U1 gauge theory, and we couple it with, let's say, massive spinor field. These are the gauge transformations, and we group the fields. I think Olaf also had it when he discussed this U1 Higgs mechanism. He had two scalar fields and one gauge field. Here we have one gauge field, U1 gauge field, and psi and psi bar, so two spinors. And the equations of motion we will also group in this form. And then the corresponding brackets of the classical electrodynamics can be written in this way. So L1 of rho and L2 of rho and A, these two, they give the gauge transformation of your field. L1 of A and L2 of A1 and A2, they give the equations of motion, and these two, they give the second Noether identity. So this is the classical L-infinity algebra, and we deform it just by putting stars everywhere and corresponding R matrices everywhere. So this is the braided L-infinity algebra. Like I said, stars and R matrices when we change the order of fields. So for example, here A1 psi 2 and A2 psi 1, there is an R matrix here. And then following the prescription, how we define the action and the equations of motion and so on, we obtain the braided action from the L-infinity structure and the braided equations of motion. The braided action is again slightly maybe different than you would just naively expect. So there are stars here. There is a star here between the interaction. This is the interaction term psi bar A psi. There are stars everywhere, but there is one term that has also an R matrix there. So this one, maybe you would not write by hand. What is nice about this braided electrodynamics is that it remains a U1 gauge theory. So it does not become a non-abelian gauge theory like you have for a star gauge, I don't know, deformation of the U1, which means that there are no interactions of photon by itself. So there is no free photon vertex, no photon vertex if you want to quantize it later. And there are then definitely some new properties. The action is real. That is also very nice because of this R matrix term that really combined with this, it kills all the imaginary terms or the odd orders of the star product. So the action is really real by just when you expand it. Equations of motion, the second Noether identity can be written using the L brackets. It can be written in this form. These are equations of motion for the gauge field, and this is just the matter current if you want, written with star products. And then if you assume that the equations of motion for the gauge field are satisfied, then you get the conservation law of the matter current. And this matter current is, like I said, now is written with the stars. Here I have one star too many because gamma mu, there are gamma matrices, they're constant, so the star product does not see them. And then from this conserved current, we can define the conserved charge with the star products in the R matrix. And in principle, if since we are working with the Moyal twist, that I did not say in the beginning, but just for the simplicity, let's assume that the twist is Moyal. Then if there is this theta ij, 0j, meaning that we have space-time non-commutativity, then this conserved charge is not trivial, meaning that this integral, the star products do not disappear under this integral, and there might be some interesting consequences there. The other thing that one should look concerning this braided electrodynamics, it's a simple example of braided gauge theory, and one should look at the quantization. I have already mentioned that it remains in abelian gauge theory, so there are no photon self interactions. Meaning that, for example, if you want to calculate the corrections to the vacuum polarization, you would just have a contribution of the fermionic bubble. So there will be no photon bubble or tadpole. diagram of the photon like we had before in the star gauge theory. And then the question is what happens with the UV ER mixing. And that is, let's say that it is work in progress, or we are trying to understand the quantization of this braided field theories now. And it's,
Excuse me, Marija, 3 minutes. Are you awake?
in this talk trying to explain is that we can consistently also deform the concept of L-infinity algebra to a braided L-infinity algebra, and then use this braided L-infinity algebra to construct a non-commutative field theory. And these non-commutative field theories that we obtain, they are not really, sometimes they get unexpected deformations, like this example of four-dimensional gravity, where you get in the action, you get terms that you would not write just by hand somehow. These non-commutative or braided field theories, they don't reduce just to the concept of putting stars everywhere. There is a strict structure of L-infinity that tells you how these theories should look like. And in the electrodynamics, I have already said it remains a billion, and then one would like to know more about the quantization, for example. Concerning the non-commutative gravity, it's nice that somehow in the same way we treat diffeomorphisms, if you do the first order formalism, diffeomorphisms and the local Lorentz symmetries, and there is no need for the universal enveloping algebra. And like I mentioned before, no, the deformation in 4 dimension is unexpected. And the future work, we would like to understand, we would like to learn more about the quantization of these braided field theories. And we would like to understand better the idea of this how these braided symmetries act. Why? Because I skipped this part, and now since I guess I have 1 minute to say something about this. I said that we have a braided nether identity, second nether identity, and that reflects the notion that we have a gauge symmetry, and this gauge symmetry really introduces what we say interdependence of equations of motion. It gives some relations between equations of motion, saying that not all degrees of freedom are independent, you have some symmetry. The problem with braided gauge symmetries is that they don't transform one solution of your equations of motion to another solution of your equations of motion, at least not in the expected way. So if you have let's say equation of motion for the gauge field A, so this should be equal to 0, for example, and you vary your gauge field A, then you would not, because of the braided Leibniz rule, essentially, you would not obtain another, in principle, you would not obtain another solution. So somehow these braided gauge symmetries, they don't act on the space of solutions, at least not in the way that we are used to. But still they are symmetries because there are second nether identities, they relate equations of motion, and that is really something that we would like to understand better. That is one of the conceptual things. If you want quantization, we can analyze, we can try to see what happens with, I don't know, Wick theorem and so on. But this concept of symmetry that does not give you, from one solution, you don't construct another solution, that is something that needs further understanding, or maybe we should change our perspective how we go from one solution to another, because these symmetries are no longer classical symmetries. So we have to learn something more. And that is more or less everything that I wanted to say.
Thank you very much.
Okay.
Well, let's see, do we have any questions? Maybe I can ask on the very last thing you said about the variation of the equation of motion. That was a bit confusing, I think. Well, not the way you said it, but the result. Are you sure that you just don't have to redefine the parameter or something, so you actually stay on the space of solutions?
No, because I think we tried everything. There is a clash between when you between the fact that this braided gauge transformation, they have the Leibniz rule, which is braided. So it's not the usual Leibniz rule. And once you do this A plus delta A, and you expand your equation of motion in terms of A plus delta A, and you linearize this in terms of delta A, then you somehow immediately assume the usual Leibniz rule in a way. So there is a clash there, definitely. So maybe we should change this side somehow, how we want to come to another solution. Maybe that there is a problem. And maybe that is what you think by redefining a parameter or something.
Something like that, because I mean, to be able to understand this is, I mean, to just say that it doesn't work at all, it would be almost like an inconsistency to me.
I think it's related with the fact that these symmetries, they just act differently, and we have to change our perspective somehow in this.
Yeah, thank you.
Way. So let's see. That's
Peter
something.
Has a question also.
I think there was a Peter Schub who raised his hand. At least I saw it.
Yes, hello, Marija. Okay,
hello.
Thank you for this nice and clear talk.
Thanks.
So I see this is an alternative proposal for a non-commutative gauge theory, like we said, alternative to the Ciric-Witten approach. Yes. So I would like to ask you about the physics consequences. So what type of new physics do you get? And, you mentioned UV-IR mixing. Do you have some preliminary results on that?
No, not yet. Not yet. We are working on that. It's just that it's sort of obvious that since the abelian gauge theory remains abelian, there will be no this. We would not have this 3 or 4 photon vertex. So there will be no well, naively, so to say. We still have to understand this, but I cannot say anything about UV-IR mixing. That is something that we are trying to understand. What is new for sure is this action, for example, for the 4-dimensional gravity. So this is the action for the first order formalism, 4-dimensional gravity, and you have this, I don't know how many, 4 new terms. And there, also equations of motion, they are written here. So this is the deformation of the Einstein equation. And in pink, you have new terms, unexpected terms, and the torsion-free condition also has some new terms. So in these equations, even if you treat them, so you treat this classically, you would maybe ask, like to see some solutions of this, and probably, but I cannot guarantee you would get something maybe different, new, whatever. And that would be interesting to see, for example. Maybe for sure there will be some new physics in this classical part, and concerning the quantization, I cannot really comment because we don't have really, we don't have results yet. We are working on this.
Can I ask another question, or I don't know?
I guess.
Okay, with this non-commutative gravity, you know, that in the version that we two worked together on, there were some exact solutions. How about in this version?
Oh, I don't know. We haven't looked at the solutions at all, I have to admit. So this, when you say exact solution, you mean the work done by Alex, for example, and also your solution with Solodukhin, correct?
With Solodukhin, yes.
Okay, so the honest answer is that I have no idea, but I would assume that maybe something similar also happens here. Although I think, I'm not sure. I think that what you and also Alex, what you did was the second order formalism. This is the first order formalism, so one has to first solve the torsion-free condition, express the spin connection in terms of the Vierbein, and then insert this into Einstein equation, and it's a bit more complicated. This I would try to compare this, for example, with our solution for the Minkowski, for the deformation of the Minkowski spacetime that we had in this model of SO2 2.3 gravity, anti-de Sitter gravity, because we had a solution which is a deformation of Minkowski spacetime. And it would be maybe interesting to see what happens here with Minkowski. I don't know.
Right, thank you.
Welcome.
Okay, let's thank Marija again.
Thanks.
Thank you very much.
Thanks. I'm trying.
We move on to the last speaker.
Okay, I'm trying to stop sharing, but it does not work. Can I close it?
Which is Kevin Morand, who will speak about non-Riemannian geometries and singularities in double field theory. We see your slides, Kevin.
So you can see everything? Okay, good. And you can see my slides moving forward?
You can start 25 minutes plus
Okay, perfect.
questions.
Perfect, thank you very much. Okay, so first of all, I would like to deeply thank the organizers for this very nice workshop. So it's a pleasure for me, to be part of it, although in a virtual way for me. So yeah, in this talk, I would like to present some recent results that have been obtained in collaboration with Mirror Park and Jungler Park within the context of a double field theory, and more precisely between the interplay between non-Riemannian geometries in double field theory and the singularity problems in GR, for example. Okay, so before going to the detail of this, let me just provide some very basic general remarks regarding the interplay between gravitation and geometry. So if we follow the paradigmatic example of general relativity, we can distinguish between two facets of gravitational theories. On the one hand, we have a kinematical content, which encodes the geometry of the theory, and in turn, as we know, prescribes the motion of the test particles and so on. So this kinematical content can be divided into three hierarchized layers. So one first basic layer is the one of differential geometry. So spacetime is a manifold. So the structure of manifold carries some extra structures such as a tangent bundle, cotangent bundle, and so on. So we have notions of vector fields and the forms. The vector fields close from an algebra under the Lie bracket. We have also a notion of Lie derivative, which also close under this Lie bracket. So overall, we have this Lie algebraic structure, which forms a very basic layer of geometry. On top of this very basic layer, we have the metric structure, the fundamental field of the theory, which in general is given by this invertible non-degenerate metric structure, which provides the notion of space-time distance on a manifold. And given this metric structure, we can define a notion of parallelism compatible with it, usually in the guise of the Dimitrijevic connection. Okay, so this forms the kinematical content of GR. To this, we should add the dynamical content, which encodes the dynamics of the geometry. More precisely, we give a dynamics to the metric structure, which is prescribed by the distribution of matter energy content, as we all know very well, which is given by the Einstein field equations. Okay, so this, very basic remarks, provides some kind of chart in order to modify general relativity. If you want to move beyond general relativity, then these different layers provide us a chart of what we can modify. So one most, obvious possibility is to modify the dynamics by, for example, by changing the left-hand side of the Einstein field equation. Also, we can modify the notion of parallelism by introducing some torsion, like in Einstein-Cartan theory. Or what we'll be interested in here is to modify the metric structure. So one, possibility to do this is to modify this Riemannian geometry of general relativity by replacing this non-degenerate metric structure with a degenerate one. So here, a non-degenerate structure I will call non-Riemannian or non-Lorentzian, as was nicely discussed by Niels Robers in yesterday's talk, and as also will be discussed in forthcoming talk tomorrow. Okay, so the prominent examples of this non-Riemannian or non-Lorentzian geometries are Newton-Cartan geometry, which is characterized by a degenerate contravariant metric, which is non-invertible and whose kernel is spanned by a one-form psi, whose provides the notion of absolute time, if you want, on the space-time manifold. There is a dual to this Newton-Cartan geometry provided by Cauchy geometry, which somehow corresponds to the ultra-relativistic limit of GR when C goes to 0. And this is given by, the basic structure, metric structure is given by a covariant metric, again, degenerate one. Okay, so this is one possibility we have in order to modify GR. But maybe another possibility, maybe a more radical one, is to modify the very first basic layer of structure, the differential geometry one. This is precisely what happens in double field theory, where we substitute to the usual differential geometry some new kind of stringy geometry. So I will review this, briefly. So in double field theory, space-time is a double, as the name suggests. So we have some double coordinates. which can be split into, so these double coordinates span 2D dimensions, and it can be split into d-dimensional coordinates, x, tilde, and x. Same can be done for the at the level of the partial derivative. And this splitting allows to define a canonical ODD metric on our manifold, on the space. So this canonical ODD metric, defines the ODD group. So okay, so space is doubled, coordinates are doubled, but somehow we can kill half of the coordinates by introducing the so-called section condition, which holds on every field and gauge parameters of the theory, as well as products between them. Okay, so this ODD metric is really part of the most basic layer structure, the equivalent of the differential geometry structure layer, because we already need it in order to define what is the equivalent of the D derivative. So here, this is a generalized derivative, double field theory, where you see there is an additional term with respect to the usual derivative, which is obtained by raising some index using this metric. So this metric should not be thought as the metric structure, but really as a part of the fundamental geometry. Okay, so the generalized derivative close under the so-called C bracket, which is some equivalent of the usual D bracket, up to the section condition, which is really necessary, for the consistency of the theory. Okay, so all this satisfies some relations which make them some courant Dorfman algebra, as opposed to the Lie algebraic structure in general relativity. Okay, so this is the most basic layer of structure. Now we can introduce the fundamental fields of the theory, which are given by a DFT generalized metric denoted H and a dilatant field D. So we'll come back to this field later on. For now, let me just mention that we can also introduce some notion of parallelism. And in fact, we can generalize the Ricci calculus of general relativity to the so-called semi-covariant calculus in double field theory. So for this, we can introduce a semi-covariant connection, sort of equivalent of the Levy-Chipsa connection, although it does not transform exactly as a connection, but still it can be used in order to build some tensorial quantities, such as the generalized Ricci tensor and the generalized Ricci scalar. So all of these overall form the kinematical content of DFT, which somehow is an analog of the kinematical content in GR. Okay, let me say a word about the dynamics of the theory. So the DFT actions read as follows. So it is built in terms of the fundamental fields, H and D. And it is also unique in similar ways that the Einstein-Hilbert action is unique under some assumptions and number of derivatives. And the associated equation of motions can be unified in the presence of, if we add some matter, coupling to matter, this the corresponding equation of motion can be unified into the so-called Einstein double field equations, where here the indices are double indices, which generalize Einstein equation. Okay, so now if we, in order to make contact with supergravity, we need to find, to choose a parametrization of our fundamental fields. So this can be done using the usual Riemannian parametrization. So given a metric and a scalar field, we can parameterize the ODD dilaton like this. And the same can be done for the generalized metric. So if we split along with tilde and untilde coordinates in D dimensions, then we can parameterize the generalized metric using an ordinary Riemannian metric and a B field, the two form B. So the B field appears through ODD conjugation, so it can be factored out in this way. And here we have just a metric G, pseudo-Riemannian metric G, and its inverse. Okay, so if we plug this particular parametrization within the DFT action, then we recover the usual universal space-time energy action for the closed string mass sector, which is like this. And okay, as is well known as well, this action is invariant under the double diffeomorphisms, which is composed of, first of all, of undouble diffeomorphism. So here psi is a D-dimensional vector field. So we have this usual diffeomorphism, and also some B field gauge transformation. So the B field only appears through the field strength H. So it is, the action is insensitive to some shift of the B field by exact two form. Okay, so this is for DFT. Now we will be interested in the interplay between DFT and singularities. So let me, very briefly mention some, very well-known facts about singularities in GR. So we can somehow again distinguish three different layers of singularities in GR. Let me just take the Stratimetric as a classic example. So using the spherical coordinates, the Schwarzschild coordinates admits a priori two singularities at r equals 0 and r equals 2m. But as we know, I mean, the r equals 2m is only a coordinate singularity, as it can be removed by a suitable coordinate transformation. So this is only an artifact of the coordinate system that we chose. And this is not the case for the r equals 0 singularity, which is a genuine singularity in the sense that it is a curvature singularity. So of course, the Ricci scalar vanishes for this metric, but if we compute the Kretschmann scalar, composed involving two copies of the Riemann tensor, then this does not vanish, and in fact, it diverges when r goes to 0. So again, if we compute the determinant, then the determinant vanishes at r equals 0. So the metric becomes non-invertible there. So overall, this points to the fact that r equals 0 is a genuine curvature singularity, which cannot be removed by a coordinate transformation. So it's not an artifact of the coordinate system, as opposed to the r equals 2m singularity. Okay, and finally, a third notion of singularity is given by the notion of geodesic incompleteness. So this is the concept which is operant in the Penrose theorem and its generalization. So indeed, one can check that there are some geodesics which have bounded proper time only, so that they can reach the singularity with finite proper time. So they cannot be extended for arbitrary value of the affine parameter. Okay, so the Schwarzschild metric is geodesically incomplete in this sense. Okay, so now after this kind of basic remarks, let me just sum up, the main idea for this talk. So as I mentioned, so in DFT, in order to go from GR to DFT, we have to modify the underlying geometry. So this stringy geometry, as I will argue, can accommodate not only Riemannian geometries, as we saw, but also some non-Riemannian geometry. And these non-Riemannian geometries, which will play a role in reinterpretation of singularities in conventional GR geometries. So this singular spacetime can be recast as regular DFT geometries. So regular, but with a non-Riemannian twist, in a sense. Okay, I will explain explicitly what I mean by that. So very specifically, we will exhibit a class of supergravity spacetimes, which features some genuine curvature singularities in Riemannian geometry. And for this specific class, we will prove that, on the one hand, the corresponding DFT generalized metric can be made regular via suitable use of double diffeomorphism. That means that this curvature singularity becomes a coordinate singularity in DFT. And the same also for the dilaton. The dilaton is also regular. And as a direct consequence, the corresponding ODD covariant curvature tensors will all be irregular in contradistinction with their Riemannian counterparts, which are singular. Okay, and we will apply this general ansatz to some particular cases, such as Witten's black hole solution in D equal 2, some spherical solution of DFT in D equal 4, and some black 5 brane in D equal 10. And for all of these particular solutions, we will prove that they are geodesically complete. That means that for all the layers, all three layers of singularities, we will see that there are no counterpart in the DFT framework. Okay, so before going to singularities, let me just review some classification of generalized metrics and how non-Riemannian geometries can emerge within the DFT framework. So the DFT generalized metric is defined by two defining conditions. So it's a symmetric ODD element. So one can wonder what is the most general parametrization, and one can find what is the most general solution to these two equations. So if we use the splitting into 4 blocks as we did previously, then one can show that the most general DFT generalized metric is classified by two non-negative integers, we denote n and n bar, and we satisfy this inequality. So we can write the most explicit form for the explicitly the most general form of the DFT generalized metric, which is as follows. So okay, this expression is a bit complicated, so let me just factor out the B field, which again appears only through ODD conjugation. And so when we factor it out, this is what we obtain. So we can focus on just this, interpreting this matrix form. Okay, so what changed compared to the parameterization I flashed earlier is the fact that this features two metric, H and K, which generically are degenerate. So the rank of this two metric is given by D minus n percent bar. So only in the case where n plus n bar equals 0, this will be a full rank, and then we will have invertible metric, so Riemannian geometry. But for all the other cases, a priori, we have some non-Riemannian geometries. Okay, so this is the same expression again. Let me just mention a bit about the fields that are involved within this matrix form. So both H and K are a sort of matrix. So they are two indices symmetric fields. And also we have the B field, which as usual is a two-form skew symmetry. Okay, the difference between the usual parameterization is the fact that both H and K generically admits some zero eigenvectors. So they are degenerate. And in fact, there are two kinds of eigenvectors, which are parameterized by I and I bar, respectively. So the kernel of H is spanned by two sets of one forms, X and X bar, whereas the kernel of K is spanned by two vector fields, Y and Y bar. And all of these satisfy a completeness relation. So this is very analogous to what happens in Newton-Cartan geometry, where we have the same kind of completeness relation. And also similarly to Newton-Cartan and Carroll geometry, we have a boost symmetry acting on these fields, which will shift the Y and Y bar vector fields by some kind of space-like vector field. So this is the equivalent of the so-called Minet boost or Galilean boost in Newton-Cartan geometry. And this will preserve the form of the generalized metric, provided that we transform K and B also in an appropriate way. Okay, so just some additional remarks regarding this classification. So obviously, different choices of n and n bar will yield some different parameterizations of the DFT metric. And the 0,0 case reproduces the Riemannian ansatz, the one we saw earlier, that yields supergravity. And for all the other cases, the induced metric structure is degenerate. So we have some non-Riemannian geometries appearing for all the other cases. Okay, so we can include some non-Riemannian geometries within DFT, so it allows to go beyond supergravity. So one additional feature of this non-Riemannian geometry is the fact that upon a generic n and bar background, then we have a kind of freezing phenomenon. So if we plug this ansatz into the geodesic equation for particles and strings in DFT, which are written in terms of the generalized metric. So if we plug this parameterization, then we saw that the free particles will freeze along these non-Riemannian directions. So, I mean, in Newton-Cartan terms, that means that there is no time-like dynamics for the free particles. So all the motion is space-like. And similarly for strings, one can show that strings become chiral along n directions and anti-chiral along n bar directions. And as we see, this is a feature that will appear somehow in for some particular space-time structure in GR. Okay, so this classification is pointwise. That means that the n bar type of a given generalized metric can vary according to the space-time point. In fact, it is not dynamically protected. So a solution to the DFT equation of motion can have a different n bar type depending on the point we're considering. However, the trace should remain invariant. So this difference n minus n bar should stay fixed. So that means that the minimal non-Riemann deviation we can have from a solution which is Riemannian at some points is 1,1. And indeed, this 1,1 has been found to accommodate some non-relativistic theories, such as the Goldmith-Oguri string or Newton-Cartan and Carroll in the ambient formalism. Okay, so let me now introduce the main ansatz that we are interested in. So this is a supergravity ansatz in t dimension, where x mu can be divided in t coordinates t, y, and zi. So the metric is given by this, where j is the regular metric. So here the only source of singularity is given by this 1 over f. Same thing for the Cabremont field, where we have this source of coordinate singularity given by this f, whereas this beta minus beta mu nu is a regular, and this is the form of the t data. Okay, so this ansatz encompasses the previously mentioned examples. So the one I showed earlier, such as Witten black hole solution and so on. Hopefully, there are more examples that we didn't consider. As I mentioned, the only source of singularity is when f goes to 0. So this clearly features the coordinate singularity. But it's also, in fact, a curvature singularity, as we can check by computing the determinant. So the determinant of the metric G we blow up when f goes to 0. And also generically, this metric features a curvature singularity. So if we compute R, I mean the Ricci scalar or the Kretschmann scalar, both of them generically blow up when f goes to 0. So we have a genuine curvature singularity in our supergravity answer. Okay, so now the idea is to just plug up, plug this ansatz into the usual Riemannian 0,0 parametrization, the one we used earlier to yield ordinary supergravity. So we plug this expression into this parametrization of the dilaton and the Generalized metric. And what we obtain by doing so is given by this expression. So first of all, we notice that the ODD dilaton is regular. In fact, f does not appear in the dilaton expression. Only the regular function psi and g. Also, the Generalized metric will have a kind of complicated expression, but it can also, as usual, be factored out. So we can factor out the beta part of the B field, like this. So we can focus on this H naught, which is given by this expression. So in this expression, sigma 1 and sigma 3 stand for the Pauli matrices. And f only appears through a positive power here. So let me write again this expression here and make some additional comments. So as I mentioned, in fact, the coordinate singularity is absent from the ODD fundamental variables. That is, there is no negative power of f which appears, right? So the dilaton does not know about f, and in the Generalized metric, f only appears through a positive power. So this is an important observation that had already been made in these earlier works, which focus on some particular examples of this of the ansatz we are considering here. Okay, and an interesting point is the fact that when in the limit when f goes to 0, then this Generalized metric becomes non-Riemannian of type 1, 1. So since it's of type 1, 1, it can be parametrized using the variables that we showed earlier, using this hk, which obviously are degenerate of rank d-2, and they are kernel or spanned by this one form x and x bar, and y and y bar respectively. Okay, so just to repeat what I said, so the n and bar type of this Generalized metric H depend on the space-time point. Okay, so it is Riemannian everywhere when f is different from 0, so of type 0, 0. And it becomes non-Riemannian of type 1, 1 at f equals 0. So in a sense, what this does is to trade the usual GR limit when f goes to 0, that is, we go from a regular spacetime to a singular spacetime. So this limit is traded in DFT with a limit from a Riemannian to non-Riemannian. But all of this remains regular. So this limit becomes a regular limit within the DFT variable. Okay, let me emphasize that the Kerr-Bremont field plays a crucial role in the regularization of this H, so in particular this part. And when this part is pure gauge, then in fact the curvature singularity of the geometric is eliminated through a double diffeomorphism. So this is when this is pure gauge, this is just acting through a double diffeomorphism, and then the curvature singularity becomes somehow a coordinate singularity in double field theory. Okay, so our fundamental variables are all regular. So both the dilaton and the Generalized metric are regular. That means that all the ODD symmetric curvature that we are going to build from these ODD fundamental variables will all be regular. So in particular, the Generalized Ricci tensor and scalar will be regular. So there is no trace of curvature singularity within the DFT framework.
Excuse me, Kevin, a few minutes.
Sorry?
Left.
I only have a few minutes, you're saying? Okay, I will be brief. So, okay, just, again, there is no determinant singularity because, this ODD defining condition for H sees the determinant to be 1. And, okay, let me skip it. Okay, so this is consideration for all the, for the generic ansatz we're considering. Now, in order to analyze geodesic completeness, we have to focus on some particular example. So we did focus on these 3 particular examples and analyze the geodesic completeness. And we show that indeed the geodesic are complete outside of this non-Riemannian sphere that appears in this example. Also, we check that the corresponding geodesic deviation remains regular. So the curvature can contain singularity, but still this combination is always regular. And also from the generic behavior of particles and strings in non-Riemannian diagrams, then we expect that geodesics will freeze on the non-Riemannian points when f equals 0, and that strings become chiral. And indeed, we explicitly verified in this example that this is okay. So let me just flash this example for d equal to Berkover. So this is the metric of Witten, and h equals 0. That means that the B field is pure gauge. And so we have a non-Riemannian, we have a hyperbola, which is a singular, right, when f goes to 0. So indeed, the Ricci scalar blow up at f equals 0 on this hyperbola. So the H flux is trivial, but still we need to introduce some pure gauge B field in order to eliminate the singularity in the DFT metric. So the resulting generalized metric is non-Riemannian regular on the hyperbola. Okay, and we also can check that we have this freezing phenomenon. So the null geodesics approach the hyperbola, but we freeze. So they will have vanishing velocity when they approach the singularity, which they do only at future infinity. Okay, and also the geodesic deviation remains regular. Okay, let me skip this and just conclude. So, okay, the main point I wanted to emphasize the fact that by exploring the non-Riemannian sector of the wave theory, so allows to go beyond, we can go beyond supergravity and accommodate some non-relativistic physical theories. But also this can be used to shed some light on some old issues within general relativity. So what we did is to identify a class of singular supergravity spacetimes as regular DFT geometries. And we do this by reanalyzing the 3 years of singularities from a DFT perspective. So as we show, the curvature singularity in Riemann geometry appears as a coordinate singularity within DFT, which can be removed by this double diffeomorphism, more specifically by this B-field gauge transformation. There is no sign of a curvature singularity, so all the DFT curvature tensors are regular. And also, by focusing on some particular known supergravity solutions, we show that the non-Riemannian points f equals 0 form some impenetrable sphere where particles freeze and strings become chiral. So we see this feature of non-Riemann geometries appearing within this Riemannian context. And computing the string frame, the geodesics outside this non-Riemannian sphere are complete, and there is no singular deviation. So this is regular. Okay, so this somehow allows to, again, the main point is that when we switch from the geometry of GR to the geometry of DFT, somehow we can address this singularity problem, at least for this particular class of supergravity spacetime. And this is already at the Cascade level. So we don't need any alpha prime expansion in order to cure this singularity problem at this level. Okay, I'm sorry for the delay, and I thank you for your attention.
Thank you very much. Questions? Do you have any questions from? No. Nothing. Sorry, Kevin, there are no questions.
Okay, it's okay. No problem.
Thank you again for a nice talk.
Okay, thank you.
And that's it for today.